The national parks of Canada not only play an important role in preserving the natural beauty of wildlife and ecosystems of our world, but also provide the opportunity for country and city dwellers alike to spend time away from the hustle and bustle of larger metropolitan areas. Places like Banff National Park in Alberta, Canada, are able to sustain this fine balance of equilibrium, maintaining and preserving the elegance of the Canadian Rocky Mountains, while also acting as a gateway away from a typical Canadian urban lifestyle. The Steel Bridge team at Western University has designed a new bridge crossing over the Bow River in Banff, Alberta, as part of the feasibility study being done by the CISC and CSCE. Our functional scale model steel bridge will satisfy the required stability, strength, and serviceability checks using appropriate lateral and vertical loads. In this video, our team will present the design, analysis, fabrication, and construction aspects of our steel bridge.
Our bridge consists of a modified Parker truss built with a combination of square and tube HSS members. It will cost just over $11,700,000 and it will take approximately 18 to 20 minutes to build, with about 2 to 4 builders on each side. Our team's success can be traced back to the beginning of the design and analysis process of this year's bridge. Rather than keeping the design and analysis separate, our team decided to take an iterative approach, integrating the two processes together and following an iterative process throughout, and justifying our decisions based on immediate software analysis as well as appropriate deflection and capacity demand ratios. We began the analysis process with hand calculations for the 6 load cases provided on a simple beam bridge design. At the same time, bridge design ideas were brainstormed based on the calculations produced in our 2D analysis. Our team put particular emphasis on 3 design alternatives: a simple beam bridge design, a Pratt truss design, and a Parker truss design. Further analysis on these designs were done to determine their feasibility on this project, including rough calculations on how much material were needed for each, as well as their approximate deflections based on our hand calculations. Based on our analysis, the Parker truss was the most feasible, giving us the most efficient design, as well as the most aesthetically pleasing with its overhead arch. With the Parker truss finalized, our team proceeded with the software analysis of the design, utilizing SAP 2000 as our primary tool to model the bridge. An envelope case was developed within the SAP model to better help us analyze the deflections and eccentricities caused by the load cases. One feature that our team put particular emphasis on during the SAP 2000 analysis was the utilization of the auto-select lists for material choice. This acted as a good starting foundation for our team's material and member proportion analysis. This function not only helped us better understand our calculations in weight, cost, and strength, but also helped us better understand what the fabrication process of the members were going to be like. Our team utilized SolidWorks to design the connections of the members. Once members were selected and proportioned, a detailed design and connection design was carried out. To reconcile the complicated geometry of the Pratt truss with dimensional constraints and clearances, as well as the connection specifications, we took a 3-step approach. We first started off with rough hand sketches to brainstorm ideas. From the ideas, we decided on general connections and produced more detailed hand sketches based on the selected designs, and once the drawings were finished, we modeled the connections on SolidWorks and finalized the geometry and measurements. As a precautionary step, our team took the opportunity to strength test our connections in our structural lab at campus. This let us know the feasibility of our design and whether or not to proceed with the build.
Our fabrication process began with importing the SolidWorks design into AutoCAD to produce the necessary orthographic drawings needed to begin fabricating. Due to the complexity of the design, we knew that some preparation prior to shop work was required. A detailed work plan was developed to ensure maximum efficiency of our time while in the shop. Simultaneous work on cutting, filing, and drilling was done to prepare the material for the welding process, for which our team was the bottleneck of the operation. Much of our design was centered around our ability to fabricate, since any design that was too difficult to fabricate was simply not feasible to create. Overall, the fabrication process was deemed by our team a success, and that model you see now is the product of many hard hours of work in the shop.
Since construction procedures and site layout are integrally linked, our bridge is designed with critical connection points away from the inaccessible areas in the center of the bridge. Our easy-fit bolted connections make it possible for laborers of all skill levels to assemble the bridge, and we take full advantage of available tools to provide a unique tension-based temporary shoring system to ensure safety and stability during all phases of construction. Our intentional top-bottom chord sequencing ensures that builders will never have to support more weight than they can safely handle, and ensures that construction loads due to temporary support conditions and lack of bracing never exceed the strength capacity of the members themselves.
More than ever, innovation and ambition in the design of today's world is required to keep up with the demands of our society. The integration of a new pedestrian bridge at Banff National Park should not be seen as simply another civil engineering project, but rather a piece of humanity finding its place in the natural world. The Steel Bridge team at Western University is confident that our bridge design is best suited for the Bow River at Banff National Park.